Dear students, our session this evening is about Euclidean geometry, and we shall start by revising the theorems that you might know. So we know that you have theorem number one. Theorem number one talks about the line drawn from the center of the circle perpendicular to the chord bisects the chord. And this is the diagram that represents theorem number one. Hope you can see it clearly. And the proof is indicated there. So the aim of the proof is to show that our AR is equal to RB. And that's the proof as it appears. I'll not go much into the proof because of the limited time we have. Every theorem has its converse. Every theorem has its converse. So the converse to our first theorem is that the line drawn from the center of the circle to the midpoint of the chord is perpendicular to the chord. And this is the diagram for the converse of the theorem. So it's important for you to distinguish between these two diagrams, the diagram representing the theorem and the diagram representing the converse. So if I may sketch both of them in this space. So for our theorem, if this is center O and we have our chord AB, then we have a line OP from the center perpendicular. So that's the diagram for the theorem. Then for its converse, the diagram looks like this. So our O is the center, AB is still the chord, and then we have OP. But then with the converse, it is indicated that AP is indeed equal to PB. So that's the difference between the diagram for the theorem and the converse. So when you look at the question, you need to be very, very careful whether it is representing the theorem or it is illustrating the converse. The converse has no proof that is examinable. Then we go to theorem number two. Let me admit these three people here who are waiting. So we go back. So theorem number two. The perpendicular bisector of a chord passes through the chord, rather passes through the center of the circle. So if you have a line, for instance, our line QR that is perpendicular to our chord AB, and it is bisecting the chord, meaning it is dividing it into two halves, where AR equals RB. So that simply means that our line QR should indeed be passing through the center of the circle. So when you look at the text in green, if QR is perpendicular to AB and that AR equals RB, then the center of the circle lies along QR. So that's basically what theorem number two is about. And if you're to prove, you need to know the aim. So the aim is to show that the center O lies somewhere on line QR. And this is the proof that I'll not go into details, but during your free time, you go back and revise about it. There's an important note here for everyone. It is important that you understand the difference between theorem one and theorem two because they are confusing to many learners. So you need to pay attention between theorem one and theorem two. Well, they are somehow related. They are somehow related. Then we go to theorem number three. Theorem number three, which is the favorite to many candidates. says that the angle subtended by an arc at the center of the circle is equal to twice the size of the angle subtended by the same arc at any point on the circumference of the circle. So with the illustration, we have our angle C subtended by arc AB. So arc AB subtends angle C at the circumference, and the same arc AB subtends angle O, if I can call it O1 at the center. So according to the theorem, our O1 here should actually be 2 times the size of angle ACB. Now these are the different illustrations. So illustration 1, illustration 2, and illustration 3. With illustration 2, which is in green, the arc is actually subtending a reflex angle, meaning an angle more than 180. So it is subtending a reflex angle at the center, and then also subtends an angle at point C on the circumference. So still our angle at C should be a half of angle O1, or angle O1 should be 2 times the angle at point C. Allow me to admit these others. We go back and look at diagram 3. With diagram 3, our arc AB actually subtends an acute angle at the center of the circle, and then also subtends an angle at point C on the circumference. So still, according to our theorem number 3, angle O1 should be twice the size of angle ACB. So that's what theorem number 3 is about, and this is the proof of it. Please find some time and go through the proofs as the teacher gave them to you in class, or as they are well stated in the textbooks and other revision materials. We go to theorem number 4. It's about the angles subtended by the chord on the same side of the chord at the circumference. These angles are equal in size. Actually, theorem 4, this is the theorem of angles in the same segment. So chord AB, hope everyone can see chord AB, subtends an angle at point C on the circumference of the circle, and also subtends an angle D on the circumference of the circle. So angle C is indeed equal to angle D, angles in the same segment. So angles in the same segment by the same chord. The proof, it's there. Hope everybody can see it. So still you have to go through it. So theorem number 3 has a deduction, which is a corollary, which talks about equal chords subtending equal angles. So chord AB equals chord CD. So since they are equal and they subtend angle F at the circumference and angle E at the circumference, the angle F should be equal to angle E. So that's according to the corollary of theorem number 4, or the deduction. Then we go to theorem number 5. It's for a cyclic quadrilateral. The opposite angles of a cyclic quadrilateral are supplementary. Supplementary means they add up to 180 degrees. So in this situation, when you add angle A and angle C, they should give you 180 degrees. Similarly, angle D plus angle B should give you 180 degrees. So that is with a cyclic quadrilateral. Then its proof, I would just display it, but you do that during your free time. So that's a proof. Our proof was to show that angle A plus angle C are actually equal to 180 degrees. And please find some time to go through the proof. And remember that every proof starts with a construct. So if you do not show the construction, no matter how neatly and nicely you write, you get 0 out of the mark. Then the converse to the side, to our theorem number 5, which is of the cyclic quadrilateral. A quadrilateral is cyclic if and only if its opposite angles are supplementary. So in the first situation with the theorem, we already know that the quadrilateral is cyclic, meaning its vertices are touching the circumference of the circle. So we already know. So if we already know that the quadrilateral is cyclic, then obviously the opposite angles would add up to 180 degrees. But then sometimes we just see the quadrilateral and we don't know whether it is cyclic. We don't know that it's cyclic. So in that situation, we can only tell that it is cyclic if the opposite angles add up to 180 degrees. Then the corollary, which is the deduction, that is the exterior angle. The exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. In other words, angle C1, which is exterior, should equal to the interior opposite. That is angle A. Note that the correct order of the words is interior opposite. This is the order in which you should write the words, not saying opposite interior. If it is opposite interior, then that is wrong. It is always the interior, because from angle C here, C1, we first enter, so in the interior, then we focus to the opposite. So that's why the order of the words should be interior first, then opposite, meaning the exterior angle of the cyclic quadrilateral equals the interior opposite angle. Then 3 ways to prove that a quadrilateral is cyclic. Way number 1, or approach number 1, you have to prove that the angles subtended by a line on the same side of the line are equal. In other words, we have to prove that angle D here equals angle C, since both of them are subtended by AB. So if you succeed in proving that D equals C, then that means the 4 corners, which is A, B, C, D, would actually form a cyclic quadrilateral. Then case number 2 is the popular one. Prove that the opposite angles of a quadrilateral are supplementary. So you have to prove that when you add angle A and angle C, you get 180 degrees, or when you add angle B and angle D, you get 180 degrees. Then approach number 3 is about the exterior angle. You have to prove that the exterior angle of a quadrilateral is equal to the interior opposite. So you have to prove that our angle C1 here is actually equal to angle A. So those are the 3 ways you should always look out for when you're asked to prove that a particular quadrilateral is indeed cyclic. Let's go to theorem number 6. Theorem number 6 is about the tangents drawn from the same point. 2 tangents drawn to a circle from the same point outside the circle are equal in length. So in other words, AB equals CB, because they are both tangents drawn from the same point B. And then the proof starts with a construction. So you can see that from my diagram above, I've constructed a line from A to O, then C to O, then O to B. and that construction gives me two triangles. Triangle AOB, which is on top, and triangle OCCB. And the proof, I'll just display it, so please find some time and go through it. Then theorem number 7. The angle between the tangent to a circle and the chord drawn from the point of contact is equal to the angle subtended by the chord in the alternate segment. And this is the diagram here. So our angle C1 should equal to angle A. So this is the tan chord theorem. And the aim for the proof is to show that our angle C1, which is BCD, equals angle A. So construct a line from B to O, then O to C, and the proof is indicated in the red there. So please, during your free time, you should go through the proof. Then the converse. If the angle between a line and a chord equals the angle subtended by the chord in the alternate segment, then the line is a tangent to the circle. So that's the converse to the tan chord theorem. So with that review, let's go straight to the application of questions. We have the first question, which is question number 7. In the diagram, PQRT is a cyclic quadrilateral in a circle such that PT equals TR. So our P, Q, R, T, and definitely back to P is a cyclic quad with our PT equal to TR. PT and TR are produced to meet in S. So point S lies outside the circle. TQ is drawn. SQP equals 70 degrees. So SQP, that is Q1 plus Q2. So the whole of Q1 plus Q2 is 70 degrees. So looking at the diagram, we don't have a tangent. So I shouldn't expect anyone to talk about the tangent because we don't have a tangent there. There is no tangent at all. First question says, calculate with reasons the size of angle T1. So where is T1? T1 is here. T1 is actually an exterior angle to our cyclic quad PQRT. So if you look at it carefully, that cyclic quadrilateral, if I can resketch it, it's like that. So this is where we have our angle T1. You can see that it's the exterior angle, and according to the deduction, this exterior angle should equal to the interior opposite angle, and that is our angle Q1 plus Q2. So definitely that shows that angle T1 is equal to 70 degrees, and the reason is exterior angle of a cyclic quad. So we fill into the diagram. Then we go to Q1. Q1 is here. Q1 is subtended by chord PT. So PT subtends our Q1. So from P, you go to Q, then to T. So PT subtends Q1. But PT is equal to TR. PT equals TR. PT is equal to TR. And remember from our theorems and their corollaries, equal chords will always subtend equal angles. So this shows that our angle Q1 is indeed equal to angle Q2. And since Q1 plus Q2 add up to 70 degrees, so that means our angle Q2 would be 35 degrees, and also Q1 would be 35 degrees. So that's the analysis that we have used to get the value of angle Q1. So we can state that our Q1 is indeed 35 degrees. And the reason is that equal chords subtend equal angles. So it's equal chords, semicolon, equal angles. So you don't have to write the whole sentence that equal chords subtend equal angles. No, equal chords, equal angles, as simple as that. So let's move on to the next question here. Let's see who are in the waiting room. We admit them in. For those of you who joined on time, thanks for being patient with the latecomers. The latecomers, next time, try to keep time. Time is everything. So question 8 here. In the diagram, PR is the diameter of the circle center O. So PR here is our diameter with a center at O. ST is a tangent. So in this situation, we have a tangent which is ST to the circle at point T and meets RP at point S. Point S lies outside the circle. Angle SPT is X, so it's this angle here, and angle S is Y, so that's what we have. So basically trying to analyze the diagram, if you have a diameter, know that a diameter subtends an angle of 90 degrees at the circumference of the circle. In triangle SPT, so when you focus on the triangle, so we already have our S, which is Y, and P, which is X. So definitely to get this angle here, so that to be 180 degrees minus your X plus Y. So that's also a good analysis. So this is 180 into X plus Y when you subtract. Then also, the triangle has an exterior angle here, which is that angle P. And then angle R here should definitely equal to our angle. If we call this T1, would definitely equal to T1 according to the tan chord theorem. So that is the analysis of our diagram. And let's go see what the question really wants us to do. Okay. The question asks us to determine with reasons y in terms of x. So we need to express y in terms of x. Y in terms of x. So what do we so far know, or what do we so far have? Angle R, we know that angle R would definitely equal to angle T1. That's according to the tan chord theorem. But our T1 was analyzed as 180 degrees minus brackets x plus y. That's according to sum of angles in a triangle. Sum of angles in a triangle. So what else do we have? Sorry, the latecomers. So that's the information so far we have, but our aim is to express y in terms of x. So now focus on triangle PTR. I'll try to sketch it here. Triangle PTR. So T is 90 degrees there. This is R, which is of course 180 minus into x plus y. And then this is point P, and then we have angle x. So in the triangle, we can see that our 90 degrees, which is at T, plus T1, which is 180 minus brackets x plus y, should actually equal to x, which is the exterior angle of triangle PTR. The 90 degrees at T plus our angle R should equal to angle x, which is the exterior angle. And now we have managed to create an equation in terms of x and y. So therefore, we shall have to apply algebra in that particular case. This is what we have. So algebra, I know some candidates are struggling with algebra, so I'll go through step by step. When you open the brackets there, so 90 plus 180, that is 270 degrees. This, remember, we need to express y in terms of x, so we need to make y the subject. So I'll transpose the y to the right and transpose this x to the left. So it's minus x equals positive y. And this will be 270 minus 2x equals y. So therefore, y in terms of x is 270 degrees minus 2x. Remember, we started by finding the size of angle T1, if you still remember T1 here. T1. So after getting T1, then we apply a term called theorem to get angle R. Then focusing on our triangle PTR here, we already have R and angle T is 90 degrees. And then these two interior angles would definitely equal to one exterior angle. So let's move on to our next question. Question number 8. Question number 8. In the diagram, PQR is a cyclic quadrilateral. ST is a tangent to the circle at S. And chord SR is produced to be PQ equals QR, S1 equals degrees, and S equals 108 degrees. All the information we have it. So let's analyze our diagram. We have a tangent, which is ST. So that tangent ST must give us the tan chord theorem. We have a cyclic quadrilateral PQRS. So it must give us the exterior angles and the opposite angles of a quadrilateral. So what do they need? the size of angle Q. So where is Q? Q is actually opposite. Q is opposite S2. And since we are dealing with a cyclic quadrilateral, our S2, which is 108, plus angle Q must give us 180. So definitely that makes angle Q 72 degrees. So the size of angle Q is 72 degrees, and the reason is opposite angles of a cyclic quad. Then we need R2. Where is R2? R2 is actually here. R2 is subtended by chord PQ. But then we are given that chord PQ equals chord QS. So these are equal chords, and therefore equal chords, we know that they subtend equal angles. So that's where we shall begin from. We shall state that our angle R2 equals angle P1, and the reason is angles opposite equal sides, or you could say equal chords, equal angles, or you could say angles opposite equal sides, of course, of a triangle. So if that's true, then that means that in that triangle PQR, I'll label P1 as R2 because they are equal, then plus R2 itself. So R2 plus 72 must give us 180 degrees. So that means we shall have two R2s plus the 72 degrees as equal to 180 degrees. So that's how we are going to approach it. So the two R2s plus the 72 degrees should equal to 180 degrees, and the reason here is sum of angles in a triangle. Of course, you transpose the 72, this gives you 108, and when you divide by 2, definitely this gives you 54 degrees. So that's how it arrived to the value of R2. So let's fill in our R2. We've got it. So this is 54 degrees, and also the side is 54 degrees. What else does the question want? P2. And where is P2? P2 is down here. P2 is subtended by chord SR, and then SR meets a tangent at point S. So according to the tan chord theorem, angle S1 should actually equal to angle P2. So which means that our P2 is also 42 degrees, and the reason is tan chord theorem. So this is 42 degrees, and it is tan chord theorem. It's a tan chord theorem. Then we go to R3. R3 is there, which is an exterior angle to our cyclic quad. Let's admit R2. Those of you who joined us late, please next time try to keep time. So R3 is the exterior angle. So where is the interior opposite? Let me try to sketch our cyclic quadrilateral aside. So this is point R, and this is R3 that we are looking for. So from R3, you find yourself here at the interior, and then the opposite of the interior is actually going to be angle P, the whole of angle P, which is your P1 and P2. We got P1 as 54 degrees and P2 we've just got it as 42 degrees. So 54 plus 42, I guess that will give you a 96. So therefore R3 equals 96 degrees, and the reason is exterior angle of the cyclic quadrilateral. So basically that's how you'd go about answering question 8 step by step. There are only two theorems here, the cyclic quadrilateral theorem and the tan chord, and of course the corollaries of the cyclic quadrilateral, and also equal chords, equal angles theorem. So move on to our next question after admitting these two people. Move on to our next question. Here we are. In the diagram below, tangent KT. So where is KT? KT is here. That's our tangent KT. KT is a tangent to the circle. So KT is parallel to chord NM. Where is NM? NM is here. So these two are parallel. So since they are parallel, they will give us alternate angles. They must give us corresponding angles. They should give us the co-interior angles. So this is what we always look out for every time we come across parallel lines. So what else do we have? NT cuts the circle at L. So where's NT? So NT, okay, NT, T lies outside the circle, cuts the circle at point L. L is a point on the circumference. Triangle KML is drawn. KML, hope you can see it. So it's the triangle there. M2 is 40. So M2 is 40 degrees and MKT is 84. So MKT is actually K2 plus K1. So both of those angles are equal to 84 degrees. So what does the question want us to do? Determine, giving reasons, the size of K2. Where is K2? K2 is the angle between our tangent KT and the chord KL. According to the tan chord theorem, that K2 should equal to the angle subtended by KL on the circumference, and that is M2. So that means K2 equals M2, which is 40 degrees. So K2 equals 40 degrees, and the reason is tan chord theorem. Please remember that it has to be written as tan chord theorem. If you just write it as tan chord, it's incomplete, because the examiner will be wondering what's wrong with the tan and the chord. So always write it in full, tan chord theorem. So in order to earn a full mark for the reason. So we've got our angle, we fill in 42 degrees. Then N1 is here. So N1 is subtended by chord ML. ML subtends angle N1. But then the same NL subtends angle K1. So K1 and N1 are subtended by the same chord ML. So which means these two angles are equal to each other because they're angles in the same segment. So already we have K1 plus K2 as equal to 84. And since K2 is 42, that means K1 will definitely be 42. And now that K1 is 42, definitely angle N1 is 42 degrees. So I hope you see how that comes about. So we indicate that our angle, which angle is that? K1 is 42. So K1 is obviously 42 degrees. I think I made a mistake with K2. K2 is supposed to be 42 degrees, not 40. Sorry about that. It should be 42 degrees, not 40. It should be 42 degrees and not 40. And now that N1 equals K1, which is equal to 42 degrees, you can say that N1 equals K1, which equals 42 degrees. And the reason here is angles in the same segment. Angles in the same segment. Now let's look for angle T. Angle T is here. That's what we need. So angle T, is in triangle KTL, is in triangle KTL. And what else do we have? Remember, we're given that KT is parallel to NM. So this is NM, if you follow that. So we're given that these two are parallel, and when you follow TN, you're actually creating a Z within the parallel lines, and that is our N1, which is 42 degrees. So definitely you can see that now our angle T is also 42 degrees, alternate angles. So this is 42 degrees, or we can state that it is equal to our N1 now, which is 42 degrees, and the reason is alternate. That's the abbreviation, the official abbreviation, alternate angles, and you need to specify the parallel lines. Writing alternate angles alone does not give you a mark for the reason. So you have to state the parallel lines, and our parallel lines here are KT being parallel to NM. So T equals N1, which equals 42 degrees alternate angles, and that KT is parallel to NM. Angle L2, where's L2? L2 is there, which is actually an exterior angle to our triangle KTL. So triangle K2 there, which is 42 degrees, angle T, which is also 42 degrees, and this is angle L2 that we are looking for. So you can see that L2 is an exterior angle to triangle KTL, and you know that the exterior angle of the triangle equals the sum of the two interior opposite angles. So this would be 42 for K2 plus 42 for T, which is 84 degrees. And the reason is exterior angle of triangle. And which triangle are we talking about? It's triangle KTL. So when you specify the triangle, it makes easier for whoever is trying to evaluate, or whoever is trying to mark you. It makes it easier for them. But okay, you're focusing on triangle KTL, then they'll see exactly what you saw. Then we need L1. So this is 84 degrees. Now we need L1, which is down at the bottom. We need L1, which is at the bottom. Yeah, let cameras are still popping in. No problem. We shall admit you all. Okay, so we need L1. Now we need to analyze. Where is L1? L1 is in our triangle K, M, L. Hope you can see the triangle there. I'll try to sketch it down here separately so that we can use it extensively. There. And that's what we have. So this is K, and it's K1. And then this is L. L has L2 and the L1 that we are looking for. And M, it's the M2 that we need. So our K1 was got as 42 degrees. And L2, we got it as 84 degrees. And angle M2 was given as 40 degrees. And we know that angles in a triangle, all of them must add to 180 degrees. So you can see that your L1 plus the 84 degrees plus the 40 degrees plus the 42 degrees must equal to 180 degrees. And it's the angle sum of the triangle. It's the angle sum of a triangle, or sum of angles in a triangle. So when you play the algebra, this will be your L1 equal to 180 minus all of those angles, which I think to be 168. 168 or 100 and so this leaves you with L1 as equal to 12 degrees. This is 58, should be. And then you can do the algebra. I'm not so sure, but I know the angle should be 12 degrees. So that's how the candidates were supposed to approach that particular question. Remember, with Euclidean geometry, every statement must go with a valid reason. Every statement must go with a valid reason. And since you have diagrams, for every value you calculate, always fill it in the diagram, because when it is recorded into the diagram, it makes it easier for you to interpret the rest of the unknown angles in the diagram. Let's move on to 8.2. In the diagram below, AB and DC are chords of a circle. So AB, yes, you can see AB there, and DC, yes, these are the chords. E is a point on AB, so that's point E, such that BCD is a parallelogram. This one here, a parallelogram. So this means that you need to know the properties of a parallelogram. You need to know the properties of a parallelogram. These properties were taught to you in grade 9, grade 10. Of course, in grade 11, it was just a revision of the properties. But I'll take you through the revision of these properties before we can answer the question itself. So this is a parallelogram. I'll just sketch it merely. Okay, so with a parallelogram, we know that the opposite pairs are parallel and the opposite angles must be equal. Okay, so AB should equal to should be parallel. So AB should be parallel to CD, and also AD should be parallel to BC, and also angle A should be equal to angle C, and angle D should be equal to angle B. And also the opposite sides are equal in length, which means that our AB equals CD and also AD equals CB. And the other properties about the diagonals, yeah, so the diagonals do bisect. The diagonals bisect. So that means M is a common midpoint. M is a midpoint. So that is a review of the properties of a parallelogram. So the question has indicated that BCD is a parallelogram. So let's indicate those parallel sides, and they should also be equal. So that's what we have. And with the angles, opposite angles are equal. So which means this angle C must also be equal to 108 degrees. And still analyzing ABCD. ABCD, all the four vertices are touching the circumference of the circle. And because all the four vertices are touching the circumference of the circle, so that means our ABCD is indeed a cyclic quadrilateral. And since it is a cyclic quadrilateral, then the opposite angles should be supplementary, meaning angle A plus angle C should equal to 180 degrees. Similarly, angle B plus angle D should equal to 180 degrees. So this is the analysis we have actually got from the diagram. What does the question want? Calculate, giving reasons, the value of X. So where is X? X is actually it's angle A, and we are given 108. And please note that 108 is not at the center. Point E is not the center, because that's one mistake candidates make. Point E is tempting. It's so tempting to be the center, but it is not. That is a trap. So E is not the center of the circle. It is not at all. So which means AE and DE are not radii to this circle. So we don't have the center, we don't have the radius. But anyway, let's try to play with what we have. What we have is that angle C should equal to our angle E in that quadrilateral. Okay, in that quadrilateral. So that's what we are going to use. I need space to write there. So I'll indicate that my angle C is equal to 108 degrees, and reason is opposite angles of a parallelogram. That's how you write parallelogram in short. It's the parallel lines and just the M. So angle C equals 108, and the reason is that opposite angles of a parallelogram are equal. So we've got it. And what else do we have? We have seen that angle A and angle C, these are opposite angles of a cyclic quadrilateral, which means that angle A, which is 2x plus 40 degrees, plus angle C, which is 108, should equal to 180 degrees. And reason is that These are opposite angles of the cyclic quadrilateral. Opposite angles of a cyclic quad. You can see that we have created an equation with the only unknown being x. Now we have to play the algebra. So this is 2x on the left would equal to 180 minus 108 plus 40, that gives us 48. And this would be 2x equal to 32 degrees. You divide by 2, your x would be 16 degrees. So I hope it makes sense to everyone, and you remember where we started from, analyzing properties of our parallelogram BCDE, and then using the fact that ABCD is a cyclic quadrilateral. So those are the properties that have helped us, together with the theorem, that have helped us get our size of angle x. Okay, with this question here, in the diagram below, cyclic quadrilateral ABCD is drawn in the circle with center O. So it is obvious. That's what we have. Complete the following statement. The angle subtended by a chord at the center of the circle is, do you remember? That was theorem number 3, is twice the size of the angle subtended by the same chord at the circumference of the center. So you can use the word twice, or you can use the word double, is double the size, or you can say it's 2 times. Is 2 times the size of the angle subtended by the same chord. So that is one mark which everyone must always get. That's one mark that everyone must always get. So the other part, use question 8.1.1 to prove that A plus C equal to 180 degrees. So meaning we need to use the angle at the center theorem to show that A plus C equals 180 degrees. So where are we starting from? Let us start from angle A. We are starting from angle A. Let's call it X. Angle A is subtended by an invisible chord, and I will try to draw that invisible chord. That invisible chord BD, which also plays the same role as the arc. So chord and arc are used interchangeably. So our invisible chord BD or arc BD subtends angle X at point A. It also subtends angle O1 at the center. And according to the angle at the center theorem, according to theorem number 3, according to our question 8.1.1, the angle at the center should be 2 times the size of the angle subtended by the chord at the circumference. So the angle at the circumference is X, so which means the angle at the center O1 should be 2x. But then we have O1, rather O2. O2 and O1, these are angles at a point. These 2 angles alone form a revolution. A revolution meaning that is 360 degrees. So if we have one angle as 2x, that means our angle O2 should indeed be 360 degrees minus the 2x. So we have got another angle at the center. Now that angle at the center, which is O2, is subtended by the major arc, the dotted arc. I hope you can see that arc, the dotted arc on top. So that arc there is subtending our angle O2 at the center. Now the same dotted arc is subtending angle C. Is subtending angle C at the circumference. So which means that angle C here should indeed be equal to a half the size of angle O1. So that's how we are supposed to approach this question here. And I'm going to use the space here where we can indeed look at the diagram. So since we were not given X and we are just creating it, so we need to guide whoever is looking at our work. So let angle A equal to X. So if angle A is X, that means angle O1 would equal to 2x. And the reason is that the angle at center equals 2 times angle at the circumference. And please, candidates, take note of this reason. Some candidates make a mistake of writing it incomplete as angle at center. If you leave it as angle at the center, that is wrong. Why? Because the reason is incomplete. Because there's a question mark. Angle at the center. What is wrong with the angle at the center? So that's why you have to complete it, that angle at the center equals 2 times angle at circumference. So that is our O1. Then O2 should equal to 360 degrees minus O1. And why do we do that? Because this is a revolution. It is a revolution. These two angles, O1 and O2, give us 360 degrees, which is a complete cycle, a complete turn, which is a complete revolution. So that means O2 is indeed equal to 360 degrees minus 2x. Then angle C should equal to a half the size of angle O2. Remember, O2 is at the center, and angle at the center is 2 times the angle at the circumference. So if the angle at the center is 2 times the angle at the circumference, then that means the angle at the circumference must be half the size of the angle at the center. So that's why we are stating that C equals half of O2. So which is, of course, reason being angle at the center equals 2 times angle at circumference. So that's a theorem guiding us. So that means C would equal to a half of 360 degrees minus 2x. So you apply your algebra. Remember the distributive property of multiplication. A half multiplies 360. So 360 times a half, that gives us 180 degrees minus 2x times a half, that gives us 1x, which is just x. So now we have got our angle C in terms of x and angle A in terms of x. So let's add and see if they will indeed give us 180 degrees. So angle A plus angle C, what do we get? Angle A is x plus angle C, which is 180 degrees minus x. So algebraically, you can see that your x and negative x will indeed cancel out, and this will leave you with angle A plus angle C as equal to 180 80 degrees. So that's the proof that the question wanted. So we started by letting angle A equal to a variable x, and using the angle at the center theorem, we got O1 as equal to 2x. Then using the fact that angles at the point give us a revolution, then O2 becomes 360 minus O1 2x. And then still apply the angle at the center theorem for the second time to give us angle C in terms of x. Then we add our angle A, which is x, plus angle C, which is 180 minus x, and it equates to 180 degrees. And then question 8.2, and our last question will be question number 9. Our last question will be question number 9. The questions are too many. Problem is the time. So that's why you always have to create more time. All we can do as your teachers is to give you a stepping stone. We try to push you at a certain level, but then you also have to push yourself higher than that level. So 8.2 here, 8.2, in the diagram, we have the diagram there. So in the diagram below, CD is a common chord of the two circles. So where is CD? CD is here. So CD is that common chord. Straight lines ADE and BCF are drawn. So where is A is here, D is there, and where is E? E is at the bottom here. So I hope you see that straight line ADE, and then the other straight line is BCF. Where is B? B is here, C is there, and F is there. Okay, so we have identified everything. Chords AB and EF are drawn. So AB and EF, where are the chords? So AB is here going up, and EF is in the small circle. So we have the chords. And that's the diagram. So looking at this diagram, which theorems do you see being represented? Just focus on the larger circle, only focusing on the larger circle. So on the larger circle, we have got cyclic quadrilateral A, B, C, D. Larger circle, the cyclic quadrilateral is A, B, C, D. And with the larger circle, the exterior angle of that cyclic quad will be C2 and D1. So that's the information we have about the larger circle. The cyclic quadrilateral is A, B, C, D, whose exterior angles are C2 and D1. Then how about the smaller circle? With a smaller circle, the cyclic quadrilateral is CFED. CFED. And now the exterior angles to that small cyclic quadrilateral are C1 and D2. So what we have here is cyclic quadrilateral and the exterior angles. So far that's the information we have. Let's see what the question wants us to do. The question wants us to prove that EF is parallel to AB. EF should be parallel to AB. So what we have, our AB, if I'll sketch it on the left here, and then EF somewhere there. So this is EF. So what we have, all we have are the AB, not AB, but AE and BF. So if that's true, Which angles should we look at? That means we shall have to look at your angle B and angle F. So if these two are parallel, that means these two angles should actually give us 180 degrees, co-interior angles. Similarly with angle B down and angle E. So if we can state that angle A plus angle E give us 180 co-interior, then we shall succeed in proving that AB is indeed parallel to EF. So how do we start? Let's start with angle B. Angle B is equal to which angle? Is equal to angle D1. Remember, exterior angle. Exterior angle. If I call angle BX, angle D1 will also be X. Exterior angles of a cyclic quad. Exterior angle of a cyclic quad. But now, going into the small circle or the small cyclic quadrilateral, angle D1 and angle F should be supplementary, which means angle F should be 180 minus X. Do you see that? And now, from angle F back to angle B, your X plus your 180 minus X gives us 180 degrees. And indeed, the co-interior angles are supplementary, which means, they are supplementary, which means AB should be parallel to EF. So that's how we are going to follow. So where do we start from? Angle D1 is equal to angle B. And the reason is exterior angle of cyclic quad. Since we have two quadrilaterals, it's advisable to specify the quadrilateral you're talking about, and the quadrilateral is A, B, C, D. So angle D1 equals angle B, exterior angle of a cyclic quad, A, B, C, D. There we go. But then, angle F should equal to 180 degrees minus angle D1. Why? Because these are the opposite angles of our cyclic quadrilateral CDEF. I hope you can see that. We started with D1 being equal to angle B, exterior angle of cyclic quadrilateral ABCD. Then angle F being equal to 180 minus D1, reason being opposite angles of cyclic quadrilateral CDEF. Then from here, our angle B plus angle F, what do we get? Angle B, remember, equals angle D1 plus F, which is 180 degrees minus D1. And algebraically, this leaves us with 180 degrees. 180 degrees. Alternatively, you can choose to use the X. Okay, you can choose to use the X. So if you use the X, that means you start by letting B equal to X, then D1 will be X, then F will be 180 minus X, then B plus F would be X plus 180 minus X. So from here, our co-interior angles, which is angle B and angle F, equal to 180 degrees. So from here, we conclude and say that therefore, AB is parallel to EF. But now we need to give the reason, and the reason is that the co-interior angles the co-interior angles are equal. The co-interior angles are equal. Co-interior angles are equal to 180 degrees. The co-interior angles are equal to 180 degrees. Or you could say that the co-interior angles are supplementary. And that's how to prove that AB is indeed parallel to EF. Then our last question of the evening is question number 9. In the diagram below, triangle ABC is drawn in the circle. TA and TB are tangents to the circle. The straight line THK is parallel to AC with H on BA and K on BC. AK is drawn. Let A3 equal to X. So let's analyze what we have. We have a tangent. We have tangents. Yes. So tangents. So this is TB is a tangent to a circle, and also TA is a tangent. Remember, tangents to the circle from the same point outside the circle are always equal in length. Remember that? And since we have tangents, that means we shall at some point need to use the tan chord theorem. So from what we have, you can see that angle B2 is indeed equal to angle C, tan chord, and angle A3, which is X, equals angle C, tan chord. So which means this would be X, and that will also be X. Then we have parallel lines. TK is parallel to AC. So when you look at them, there is that Z there. So K2 would equal to A1 alternate angles. And also angle K3 would equal to angle C, corresponding angles. So what else? We are looking for the easy to identify properties here. Okay, so we shall discover others as we move on. Prove that K3 equals X. And you see, why is K3 equal to X? Because K3 equals to C and C equals to A3. So that's why it is equal to X. So we state that our angle K3 equals angle C, and the reason is corresponding angles equal, and we need to specify the parallel lines. It's TK parallel to AC. So because TK is parallel to AC, but then C is equal to X, which is A3. And the reason here is tan chord theorem. So if K3 equals C and C equals X, definitely K3 would equal to X. So that's it. Then prove that AKBT is a cyclic quadrilateral. Where is AKBT? A, K, B, T. It's a cyclic quadrilateral. So if you sketched it, it's something like this, like that, and there. So this is T, this is A, this is K, this is B. So for this to be a cyclic quadrilateral, these angles must be equal. And which angles are those? That is angle K2 and angle B2. So that's what we really have to focus on in that particular case. Okay, so that's 9.2. It is a cyclic quadrilateral. 9.2. Do you even have an exterior angle to that? Yeah, the exterior angle would be K, would be K1. K1 would be the exterior angle. But then alternatively, we can also change the focus and look at angle K3. Okay, I need the space here. So look at K3. It's still the same. It's still the same quadrilateral you're talking about. I'll sketch it here. I have something like that, and something here, and that. This is my point K. So this is A, K, B, T. So TB subtends angle K3 at K. The same TB subtends angle A3. And this is X. And we also proved that this is X. So focusing on TB, you win. So you realize that it is better to focus on TB than focusing on TA. Remember, you can focus on any of the four sides. So focusing on TA would not give us proof that B2 equals K2, but then changing our focus on TB, we can indeed see that our angle A3 is equal to angle K3. And with that, and this explains why the question was only 2 marks, because the examiner saw that you're not supposed to go through a lot of hassle. So would state that angle K3 is equal to angle X, and X is equal to angle A3. And because this was proven in the question above, and therefore AKBT is a cyclic quad. Now, what's the reason here? The reason is that line subtends equal angles. Line subtends equal angles. Line subtends equal angles. Now that is a cyclic quad. Now prove that your KT bisects AKB. AKB, AKB. That's the angle. So we need to prove that this TK subtends the angle. In other words, we need to prove that angle K3 equals angle K2. Already K3 was proved to be X. So we only need proof that indeed K2 is also equal to X. Focusing on the same cyclic quadrilateral. This is our TA. TA subtends your angle B2. And angle B2 would equal to angle A2, rather K2, because they're all subtended by the same TA. So angles in the same segment. But then remember, we have a tangent at B, so which means angle B2 is indeed equal to angle C, tan chord. So B2 is X because it is equal to C, and then B2 is equal to K2 angles in the same segment according to chord TA. And now you can see that K2 is X and K3 is X, and therefore it proves that our TK is bisecting those two angles. So I'll use the space here for 9.3. B2 equals angle C equal to X, and that's according to the Turn-Chord theorem. According to the Turn-Chord theorem. But then also we analyze that K2 equals B2 angles in the same segment. B2 equals K2 angles in same segment. Angles in same segment. And you can now see that our K2 is indeed equal to K, K3 equal to X. So therefore, TK indeed bisects. TK bisects angle AK, AKB. And then 9.4, we are almost winding up. 9.4, prove that TA is a tangent to a circle passing through AK and H. So AK and H, AK and H. So with this kind of questions, it's better for you to sketch a simple circle outside and then position those points, the A, the K, and the H. So okay. So if I put my A here, then my K should be somewhere here, and then the H should be somewhere there. So that's what we have. It's a circle passing through AK, H. So which one is a tangent? Is TA. So where is TA? TA is here, there, and that's point T. And that means I have to complete chord AH. Complete chord KH. So which angle at A are we really focusing on? That should be, because we are from A to K to H. So, and the chord is AH. So we are looking at A3, which is X. So A3 here, which is X. And which K from A, K to H? A, K to H, that would be K2. 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 So in order for AT to be a tangent to this circle, our angle A3 must equal to angle K2. And we have already proved that K2 is X. Okay, so obviously we just have to state that A3 equals K2 equal to X. And the reason is that this has already been proven. And therefore, AT or TA is a tangent. A tangent. And why is it a tangent? It's because you could say converse Turn-Chord theorem. Could say the converse Turn-Chord theorem. In other words, if the angle between a line and the chord of a circle equals the angle subtended by the chord in the alternate segment, then that line should be a tangent. So that's the converse Turn-Chord theorem. I hope everybody gets that. Then the final part. And after this, we shall have a word from Hakil before we end our session. 9.5. S is a point in the circle such that points A, S, K, B are concyclic. Concyclic, meaning they lie on the same circle. Explain why A, S, B and T are also concyclic. So let's just sketch our simple circles here. The first circle shows that A, S, K, and B lie on the same circle. And then the other circle talks about the same A, the same S, and the same B. And then it talks about point T. And then it talks about point T. So when you look at these two circles, the only difference between them is point K and point T. So if AS, KB are concyclic, definitely AS, TB will be concyclic. Why? Because out of the 4 points, 3 are concyclic. ASB in the first circle is the same ASB in the second circle. So if K is forming a circle with the other 3 points, definitely T must form a circle with the same 3 points. So that explains why ASB T is also concyclic. So I can write this down. It says that the circle passing through points A, K, and B, those 3 points, contains point S on the circumference. And also the circle passing through AKB, A, K, B contains point T on circumference. So these two circles, they have AKB common. The only difference is point S and point T. So it's just obviously that T and K should be on the same circle here. So therefore, the points A, S, B, and T are also concyclic. So it's just a matter of connecting them, interlinking all of them. So this is what we've had tonight. For those of you that have been recording, please find some time to go through everything. It's been a worthwhile 1.5 hours long. It has been more than 1.5 hours, I know. So thank you for attending, and I hope that you have benefited